Okay, so I'll talk you through this one, and then obviously you'll be able to do it yourself going forward. So here we get this example. We've got an object being pushed up a slope. At this point, the slope is frictionless. It's been pushed up by force F at constant velocity. Straight away now, with what we've learned already, as soon as you see the word constant velocity, it should ring a few bells for you. What does that tell us about the net work done? 0. Okay, so we know that. What does it tell us about the force pushing it and any force working against that? They're going to be equal. Now, since there's no friction, what force could be working against that? This little parallel force. So remember these little triangles that you drew in grade 11? Got to do them again. So you've got the force of gravity straight down, and you've got the perpendicular component, and you've got the parallel component, and that's the force that's working against friction. So we know straight away that force must be equal to the force that's not friction, the pushing force. That force must be equal to the pushing force. So if we know the mass, we know the angle, we should be able to calculate that. Now with these questions, it's the same as Newton questions. If you get the question and you don't know what to do, just work out something. Find something that you can work out and work it out. And then from there, you might be able to see the next step. All right. So that's what I'm going to suggest you do. Always draw a force diagram. You got the force of gravity. You got your angle. Now we've got our little force diagram there, and we know we can work out force parallel because we know the angle and we know the mass. So the force parallel, if you remember the trig, it's going to be Fg sine 30. You all happy with that trig? Yeah? That's Fg sine 30. You know, for Fg is just mass times 9.8 and sine 30. And so that's going to give you a value there for the force parallel. So we know that. So let's now go and work out all the different works that are being done, right? We know that the net force is going to be 0 because it's moving in constant velocity. And therefore, as I said, we know that now, do you know what these vertical bars next to the thing represent? The absolute value, right? These two things are going to be, I could have written down this is going to be equal to negative of that. Instead of just written down the absolute value of the parallel force is going to be equal to the absolute value of the force. So now I can work out the work done by the force F, which is one of the things you might be asked, which is F delta x cos theta. I now know that this F is going to be equal to F parallel. And I've just worked out F parallel, so I can stick F parallel in there. And it's F parallel delta x cos theta. Now, what is the theta? Is the theta 30 degrees? This cos 30, this cos theta, what angle is this? The angle between F parallel and delta x. And the angle between F parallel and delta x, actually it's not F parallel, it's because we're talking about the force F and delta x. And the force F is in the same direction as delta x. So the angle is 0. Don't make the mistake of using theta as 30 degrees there. The 30-degree angle is a completely different angle. That's the angle of the slope. Always remember with work, the angle you're talking about is the angle between the force you're dealing with and the displacement of the object. Right. So that's the work done by the force F. What would be the work done by the force parallel? Same. Just it would be negative. Why would it be negative? Where would the negative come from? The 180. Because the force parallel is down the slope and the object's moving up the slope. So the angle between the displacement and the force would be 180 degrees. Now there is another way you can work it out. You can work it out using this delta y and the vertical distance. It actually lands up giving you exactly the same formation. If I asked you to work out the work done by gravity, all right, the work done by gravity. So is the gravitational force acting on the object? Yes. Does the object move in this vertical direction? Well, if it goes from here, if it goes from there to there, it does move a vertical distance, doesn't it? No, but in going from here to there, you have gone up by that amount. So you have done work against gravity. If you go from down here to up there, you have risen this height. So you have had to do work against gravity. You agree? So gravity has done work on you. Now what's the work done by gravity? Well, same, just apply your formula. Work done by gravity is the force of gravity times the distance moved in that direction. And the distance moved in the direction of gravity, or against the direction of gravity, is delta y.
Why is it called 180?
I'll tell you now. So you're happy with the delta y? And you're happy that it's 3 sine 30. If you're moving 3 meters here, and that angle is 30, then this height would be 3 sine 30. All happy with that? So we've got the force of gravity times the distance moved in the direction of gravity. The only problem is that you're moving up, and the force of gravity is down. And that's where the 180 comes from. Okay. The displacement in that direction is up, and gravity is down. So that's where your 180 comes from. Now, if you just look at this formula, the Fg was 2 times 9.8. You got the 3 sine 30 because that was delta y, and you got cos 180. Now you can see it's exactly the same components as you got here, except for the angle here. So it gives you exactly the same value, it's just negative. Well, we could ask you the question. I could say to you, calculate the work done by gravity. Well, if I asked you for the work done by gravity, you'd have to explain why you're using the force parallel. See, the two works are the same because it's moving at constant velocity. If it was accelerating up the slope, they wouldn't give you the same answer. So you get minus 29.4 joules. That's because the work of gravity equals the work done by the parallel force. I've just here worked it out a slightly different way, using the parallel force. And you can see that you can also say that the work done by gravity is equal to delta EP, but this is incorrect here. Let me just fix this. This last statement, the work done by gravity being equal to the change in potential energy. It's actually equal to minus the change in potential energy, and I shouldn't put the minus in there. I showed you yesterday in the example that we did that the change in potential energy of the object is equal to the negative of the work done by gravity. Is the object gaining or losing potential energy? It's gaining potential energy. So what's the change in potential energy? It's got to be positive. So the change in potential energy would be plus 29.4 joules. But the work done by gravity is working against that because you've got to fight gravity to give it potential energy. So those two are the negative of each other. The work done by gravity is the negative of the potential energy change because it's gaining potential energy. Now I know this is a subtle point, but now you're in matric. I like the way your shoes are polished. Looks good. You guys are in matric, so you need to learn to be subtle, right? Subtle things are very important. Now there's a subtle difference here. The work done by gravity is different to the work done against gravity. They're equal and opposite. Okay? The work done against gravity would be 29.4 joules. That's the work done against gravity. The work done by gravity is minus 29.4 joules. Work energy theorem, still going to hold. The net work should be 0. That's because the work done by gravity is equal to the negative of the work done by the force F. So this is minus, that's plus, and it equals 0. And that gives you change in kinetic energy, which is 0, which we knew from the start because that's constant velocity. Question?
So let's say the force of the work higher than the force done by gravity. And then there was another question that asked, what is the force done by gravity?
What is the force done by gravity, or what is the work done by gravity?
Well, sorry.
Okay, so the work done by gravity would be the same. There would just be extra work done by the force, and that would have accelerated the object.
Would you write it as force?
Yes. The work done by the force. Okay. So the force is giving the object energy, right? You got to remember, when you move an object, you're giving it energy. Question?
So just the cause, so
Yeah.
Is it so the cause is
This one.
opposite direction of the force?
This one.
Yeah. So.
Yeah, because remember, the angle that you're talking about here is the angle between the force and the displacement. And the displacement delta y was up, and the force of gravity is down.
And then
So
for the first one would be cos 0, so
because here we're talking about the force F and the delta x. Now the force F is in the same direction as delta x. So the force, the cos angle is always the angle between displacement and the force. Right, happy with this one? Now that's an easy one. There's two ways for us to make it more complicated. One is to make it acceleration. So the force, the work done by the force would be greater than the work done by gravity. Then it's going to accelerate. The other way to make it harder would be to add friction. So then the force has got to, in order to accelerate it, the work done by the force would have to be bigger than the work done by gravity and the work done by friction. I don't know why I did that one. I can't remember why I put that slide together, so we're just going to skip over it. So here's a little example. Okay, this is straight out of the notes, to be honest. It's just talking about the fact that you can work out the network two different ways. So I have showed you this already on another example. Try this yourself. Given you a gap there, put a text box in there if you're working online, or if you're doing it by hand. Just try and work out the network in this example two different ways. The first way, you do it by working out the work done by each force individually, and then you add all the works together. And this one is by working out the resultant force and adding the works together. Try it. Like a 5 or 10 minute exercise. You see the object is being moved to the right, a distance of 2 meters, by a 5 Newton force, but there's a 2 Newton frictional force.
Just minus the frictional force.
Well, there's two different ways to do it. The first one, you must work out the work done by each force, and then add the works together. The second one, you must calculate the resultant force first, or the net force, and then work out the net work using the net force. Come on, you shouldn't be sitting just staring at your screen. You should be typing away furiously.
Sure.
Is
work done by force equal to work done against gravity?
It depends if the force is working. It depends on lots of things. If the force is working directly against gravity and it's moving in constant velocity, yes.
But if it's accelerating, it won't
No.
always.
So in this first example, calculate the work done by force F1, and then calculate the work done by force F2. And then add those together. Jonty, I have turned you up if you've got any questions.
So going in the negative direction, you say negative 2 meters.
No. You're going to get the negative from the angle,
The angle, yeah.
from the 180.
So what is it W net? And then
Yes. So you work out the W1 or F1, WF2, and then W net is WF1 plus WF2. And it should be a plus answer added to a negative answer. Joules. Work is always measured in joules. Now, for approach 1 and for approach 2, you should land up with the same final answer. If you do, then you're getting somewhere.
So, approach 1.
Yeah.
You take the x to the negative.
No. You get the negative from the angle. No, so if you do take it as negative, then you're going to get a negative and a minus 180, cos 180, and that's going to give you a positive answer, and it mustn't be. It must be negative. So you don't put it in as minus 2 newtons. Put it in as 2 newtons. The negative is going to come from the cos. Yeah, you just take the absolute value of the force. Well, for F2, the delta x is that way, but the force is that way. So the angle between them is 180. And cos 180 gives you your minus. Sorry, hang on. Go. I always prefer approach 2, but you can do either. So approach 2, Nick, work out the resultant force or the net force by adding the forces together and then do the work of the net force. That's easier. So can I put approach 1 up? So you should have got 6 joules net work. And that's because the work of force 1 was 10 joules and the work of force 2 was minus 4 joules. And then your net work, which was W1 plus W2, was 10 minus 4, which gives you 6. Let's see a show of hands if you got that right. Lovely. Mr. Pillay, you made a little mistake there. What was your little mistake? Good. You didn't say the 180. Cos 180. Okay. You understand why it must be 180? Good. Mr. Dundalakis, where did you get on that? Nowhere. Why do you not know what's coming? Okay, you need to watch them, and if it doesn't got questions, either Teams message me or come to science support. You know, guys, know that science support is up and running, eh? Now, if you want that answer, there's a box over it. Just delete the box. Right, so the next one should give you the same answer. And you can see that the next one is easier, I think.
Yeah.
So I prefer to always work with a net force because that was last year's stuff. Adding up forces is dead easy. And now you got W net is F net delta x cos theta. Oh, simple. There's some questions where you can't do that because they haven't given enough information. But if you can do that, I think it's worth it. Yes. Yeah, and then remember the object moved up. If you go from here to there, aren't you rising up this height? So you're going up, and gravity was down 180 degrees. Yeah. All right. So the 5 Newton force is doing positive work on the object, and the 2 Newton force is doing negative work. Okay, this one is done for you. This is just to show you that what we mean by conservative forces. So there's the definition of conservative force. Conservative force is one for which work done by it or against it depends only on the starting and ending points of the motion, not on the path taken. It's quite a long-winded definition. You need to learn it. It often gets asked, right? You must also remember that gravity is the only conservative force that we work with. Okay? Gravity is our only conservative force. So there's never any other conservative force that we work with. All right. Okay, can you close your computer if you're not working with me on the thing? Because I don't trust you.
So how's that any different?
Now, if you drop a 5 kilogram object 2 meters and you let it roll down a frictionless surface 2 meters, the work done in both scenarios is the same. It will gain the same amount of kinetic energy. If you do the calculation, going down here, it's falling down 2 meters. So the work done by gravity, which is the only force doing the work, Fg delta x cos theta is 1. Delta x is your 2 meters, and Fg is 5 kilograms times 9.8. You get 98 joules. Let's work out the work done in going from here to there. All right?
I know it travels 2 meters down.
Yes.
It definitely travels like 3 meters.
Here. Yeah, so it's traveling further. So if you were asked to work out this delta x, you'd need to know the angle, right? And you could work out this delta x by saying cos of theta, cos of this angle, cackle would be, sorry, it's actually cos of this angle, isn't it? Cos of this angle, would be cackle and howl would be 2 over that. Cos of this angle. I don't know how you know your trig ratios. Sokotoa. I learned some old hens cackle and howl till old age. So cos is cackle and howl. It's 2 over delta x. So that means delta x would be 2 over cos theta. So once you know theta, you could work out delta x. Okay? Then, what is the force pulling it down the slope? The force pulling it down the slope, in this case, if that's your theta, would be F parallel. I'm just working with that one. Yeah, doesn't matter. So, what's this parallel? Well, again, that's going to be FG cos theta, because it's adjacent to, if you drew a 90-degree triangle there. So the F parallel FG cos theta, we know FG. Try not to talk over me, please. I know you're explaining stuff. So again, you'd have F parallel is FG cos theta. So now what's the work going to be? The work to move it from there to there. It's going to be F parallel times delta x cos theta. Well, we've just worked out F parallel, and we've worked out delta x, both in terms of cos theta. Multiply them together, the cos thetas cancel out, and you're left with exactly the same as you got here, 98 joules. Doesn't matter what that angle is, if you roll it down a frictionless surface, then the work done either way is exactly the same. Yeah, the same object. The same object, yeah.
So we evidence that what like the force of friction, what like gravity.
Yeah, so if it didn't give you the same value here, if there was friction against it, you could find out how much was missing when it got here. That would be the work done by friction. All right. You're suggesting a nice exam question there for us. Okay. Non-conservative forces. So what is a non-conservative forces? All the other forces we deal with are non-conservative. What's the only conservative force? Gravity. So everything else, friction, the applied force, okay? Anything else pushing on the object, the force of the engine, the force of the person pushing it, whatever, those are all non-conservative forces.
I don't understand what it depends on path.
So, you know, I've just showed you that if the object falls from here straight down there, you get a certain amount of work done, or if it goes this way under the only influence of gravity, different path, but the same height is covered, same amount of work is done. So the amount of work doesn't depend on the path taken. And it's only thingamabody that does that. So here's an example. A sphere of mass 2 kilograms is shot vertically upwards from ground level. Reaches a maximum height above 4 meters above the ground. Why does it only reach 4 meters? Gravity is working against it. But now there's not only gravity. A constant frictional force of 5.4 newtons acts on the sphere throughout its motion. Calculate the initial velocity of the sphere using energy principles. Calculate the initial velocity of the sphere using energy principles. So let's think a possible way through this first. If we know, do we know the force of gravity on this thing? Okay, so if we know the force of gravity on it, do we know the distance over which that acts? Yes. So could we work out the work done by gravity? Yes, we could. Now, do we know the frictional force? Yes. Do we know the distance over which it acts? So can we work out the work done by the frictional force? Yes. Are both of those in the same direction? They're both down. So as works done on the object, they should both be negative. You agree? Yeah? I'll come to you in a second. Now, what other work is done on the object? Is there a force upwards? Is there a force upwards? It's shot up. So there was a force to shoot it, but the minute it's been shot, there's no more force. So there is no other force acting on it. So will there be a net force on this object? Yes, and what's the net force going to be the sum of? Those two downward forces. So will there be net work done? Yes. If there's net work done, what can you tell me about the kinetic energy change? It's going to be equal to the net work. If the kinetic energy change is equal to the net work, and we can work out the net work two different ways, then we can calculate the kinetic energy change. Now, what was the kinetic energy at the end of this movement? 0. So then we should be able to, if we know the change in kinetic energy and we know the final kinetic energy was 0, we should be able to work out the initial kinetic energy, which means we should be able to work out the initial velocity. Now, if you understood my thinking through that, you should be able to do this. Do you want a hint? Okay, you had a question first, then I'll come to you. Okay.
So we use the,
Hang on.
when the kinetic energy equals, there's no rotation.
Okay, so no, that doesn't happen. The work energy theorem says the change in kinetic energy is equal to the net work. So try it. Here's your hint. Do you want the hint? Well, it's just what I said, but I now written it down. This is one way to do it. Work out the net force, then work out the net work, which gives you the change in kinetic energy. Then you can work out VI. Or work out the work of the one force, work out the work of the other force, add them together to get the net work. Once you've got the net work, you can work out the change in kinetic energy. Once you've got the change in kinetic energy, because you know the final kinetic energy, you can work out the initial kinetic energy, which means you can work out the initial velocity. Try it. I've taught you enough that you should be able to do it. Try it. I'll give you...
We use the equations of motion.
No. You must use energy principles. Try it. Get a piece of paper and scribble. You should be able to work out the work done by gravity now. You should be able to work out the work done by a force like friction. You know the force and you know the distance over which it's acting.
If it's work done with gravity, is it just going to be that 2 times 1?
Rather write it down.
But is it going to be that 2?
Well, that's going to be the force.
Oh, gravity.
Yes.
Okay.
Yes.
When you work out WEP equals 10 to EK, can you say EK final minus EK?
Yes. The change is always the final minus the initial. For kinetic energy. You're really asking me that.
So what?
I'm surprised you need to ask me that, since not only are you in grade 12 and you've done it in grade 10 and grade 11, but it's written in your PowerPoint about 3 or 4 slides back.
What angle theta?
Well, it depends which force you're working with. W net. Well, so what is W net made of? So the work doesn't have a direction. If when you're talking about direction, you need to be talking about the force. So which force are you talking about? So which one are you talking about? They're both down. And which way is it moving? Okay, we're going to get there. It's the work done by all the non-conservative forces. Yeah, don't use that now. I haven't shown you that formula yet. You can do, You can do, and then get the network, or you can calculate the net force and then use that to get the network. Either way, you'll get the same answer.
How would you work with net force though?
Well, how many forces are there? Two. Can't you add forces together? We did that in grade 11.
But how do I work out the force going out?
Who said there's a force going up? I thought we said there isn't a force going up.
It's shot vertically out.
Yeah, you stole my tennis ball, you bugger.
So it's on my desk.
So this thing is being shot up from this point.
Yeah.
Is there any upward force acting on it while it's moving up?
No, I was moving up.
Exactly.
Initially,
Yeah, but we're not talking about when it was shot. We're talking about from the point when it's shot. It is shot up. Now we just talk.
Just the gravitational potential energy coming down.
Not the so the potential energy isn't a force. There's gravitational force down and there's friction down. Go and answer. 10 meters per second. I'm hearing 10 meters per second. What happens to the negative? Well, how did you get, so, good question. I'll come to that in a minute. Yeah. Well, so there's two answers. One's positive, one's negative. You've got to look at them and say which makes sense. Now, we've taken up as positive, so the down possibility doesn't make sense. Negative energy. Well, if you're taking energy away from an object, we say that your work is negative. Now, that object's got lots of energy at the start. It's shot. Gravity and friction rob it of all its energy. So they're doing negative work on it, yeah. They're working against it. Can I put it up? So, no, I mustn't do it that way. I must do it this way. So watch. So I did it the easy way. I said, okay, let me work out the net force first. Net force equals the sum of the forces. Force of gravity is 2 times 9.8. Force of friction is 5.4. 2.5 newtons down. I didn't make them negative. I just know it's down, so I know what I'm doing. Then I said, W net is the net force times delta x cos 180. Why is it cos 180? Because I know the net force is down, but the thing's moving up. So that gives me minus 100 joules. So I now know from the work energy theorem that the net work is equal to delta EK. Delta EK is EKF minus EKI. But the final velocity is 0, so EKF is 0. So therefore EKI is minus 100 joules equals half mv squared. And then that gives me the square root of this, which gives me a positive and a negative answer. Plus 10 or minus 10. But I have to know that the minus 10 is ridiculous because this thing lands up going up, so it must have been positive. So you discard the answer that doesn't make sense. Questions? Sorry? I think we should take a 5-minute break. This here is a different way to do the same question. All right? I've just shown you how to do it. You two gentlemen, come and chat to me afterwards, please. I've just shown you how to do it my way, the easy way. This is a slightly different way. There's a formula that you'll see. I think it's also given in the data sheet. WNC equals to delta EK plus delta EP. That's actually just another way of representing the work energy theorem. It's actually exactly the same formula. You can change the one into the other one. I can show you that at some point. But this formula is accepted, and you can use it, and it also always works. What does WNC stand for? All the work done by all the forces except gravity. Okay? In this case, there's only one, and that's the force of friction. So WNC is the work done by the force of friction, and that's worked out. All right? Now that's supposed to be equal to the change of kinetic energy plus the change in potential energy. Change in potential energy is easy, it's just mgh. And that gives you your 78.4. And delta EK is half mv squared. You can put that in for delta EK. You can put this in for delta EP. Add the whole thing up, and you'll end up with exactly the same answer.
So can you go back to the first way that we did it?
Right, so you get exactly the same answer. You can use that NC formula. I don't like using that formula, it bugs me. But if you like it, it always works. It's just another way of expressing the work energy theorem. But I personally think this way is easier. Work out the net force and then go from there. Got it. Okay.
I don't really understand that from that third step.
The third step. You need to come see me afterwards, please. This step. Okay, so this is the work energy theorem. Okay, the net work is equal to change in kinetic energy. That you have to just learn. Now the change in kinetic energy is final minus initial. But the final kinetic energy of this object, since it reaches a maximum height, it stops when it gets there. So the final kinetic energy is equal to 0. So the net work just equals to minus the initial kinetic energy because that is 0. So you're happy with that now?
Yeah.
And then you can just put that in, you've worked it out, and then you use the formula for kinetic energy. Okay. Do you need to show it? You could kind of, as long as you do it, you'll get the mark. There wouldn't be a mark for showing it. There will be a mark. Yeah, you two gents, come and see me afterwards, please. All three of you. Doesn't matter, come see me afterwards. You have 5 minutes for your break. So there will be a mark for doing this, because you have to do that somewhere. But you don't have to. The second line?
After doing that, can we just go
straight to here?
I will just say EKK equals 0.
Yeah. Yes.
I don't get it. So why is there no force being applied?
So it's this business. The object is shot, okay, from a gun or something. But we're only considering the time in free fall. So we're considering the time after it's been shot.
Oh, so once,
Yeah.
once it's
Once it's left the barrel or whatever.
So 1.5, -1.5 last time velocity.
Because this is 100 joules, this was the net work we worked out was at minus 100, right? That was the work W net. Now, that's your minus 100, but this is equal to EKF minus EKI. Well, that's equal to 0. So now you're left with minus EKI. So it has to be minus half mv squared. Okay. Now, look, I'll come to you in a second. Essentially, these are not very difficult, but there's lots of places to make little errors. Leaving out a minus. Forgetting, some little thing, and then you get an answer that's completely out. That's why we're going to do lots of examples. Trey. Well, you're trying to work out the initial velocity. There isn't a force by it. We're only considering it has been shot. So it's already moving. We're not considering the forces shooting it. We're just considering the fact that it's been shot up, and now we're considering it from the point at which it is shot. There's no longer force upwards. So then you'd be able to then you'd be considering this motion. So that has to tell you something about this. They didn't tell us that. They just told us it has been shot. The minute we see it, it's already moving with the initial velocity. Go. Which one? This one. That's an alternative method for the same question.
Sir.
Yes. So this wouldn't be more than 5. No. It might even just be 4. I mean, you normally get 1 for doing something like this. You get 1 for that. You'll get another 1 for this bit. You don't get a mark for the answer. You just get a bit mark for doing the work. Then you'll get 1 for this. So that's 2, 3, 4, 5.
Do you not get a mark right out for me?
No.
No.
Not the F delta X cos theta, no. You get a mark for using it correctly. You might get 1 mark for it once, so potentially 6 marks, but I doubt it. Okay, try this one.
So,
Yes, Jonty.
what if in an example the force which is applied on the object changes?
No, we won't give you that.
Okay.
If we do, we'd have to ask you to do those 2 sections separately. So when it was this big and when it was that big.
Okay, so it wouldn't accelerate or anything.
Yeah. Let's try this one. You got a horizontal force of 4 newtons, pulling a block, changes its motion on a frictionless surface. Nick, been rude. The block's velocity is 3 meters per second when it passes point S. What is its velocity when it passes point D? Using energy principles. Now we're saying that it changes its motion, so it's not at constant velocity. Its motion changes.
So you can't use that F from that.
You must. You've got to use work energy principles.
But if it changes,
Changes its velocity. Well, if it changes its motion, then you're going to get a change in kinetic energy.
yeah, so but then would that be a change in force then?
No, the force is constant over the 10 meters.
Oh, okay.
Try it. Try this example. It's exactly the same as the other one.
Is it
Marcus, you are asking me to give you demerits, and you're in matric. I don't want to do that. I would find that if I was you, I would find that quite insulting, I think. I don't know why. It's never going to get any easier if you don't try. You just can scroll through your phone. You only got one force. So the work done by that force will be equal to the net work.
Network also equal change in
Kinetic energy, always. Change in kinetic energy.
only kinetic energy.
Yes, that's the work energy theorem. You've got to learn it. The work done by this force must be equal to the network. And you know the network must be equal to the change in kinetic energy. You should be able to calculate the initial kinetic energy because you know the initial velocity. So where do you start? That's fine.
Yes, sir.
So what's the force?
So the force is 4 newtons.
So next row. 4 times, what's delta x?
10 meters. So,
There we go. And what's cos theta?
so it's working in the wave direction, so then essentially it's 0. So,
Cos of 0,
yeah,
which is
1.
1.
Yeah.
So now you've already calculated
Yes.
the work done by the force F. Don't just say W, it's W work done by F,
Oh,
WF. Are there any other forces on it? Frictionless, which means that work done by force F is the network.
yes.
Now don't we know the kinetic energy, the work energy theorem? Network is equal to change in kinetic energy. Can't you work out the initial kinetic energy because you know the initial velocity? Kinetic energy. What's kinetic energy formula? Yeah. Yeah, and you know the initial velocity, don't you? So you can do that. If you know the initial kinetic energy, and you know the change in kinetic energy, you should be able to work out the final kinetic energy. Anybody got a number for me? 7. You got 11. Okay. Square root of 11. It's not going to be 7. How much you get, Adam?
I bet the house on the 7.
Sorry?
I bet the house on the 7.
Oh, you left the house at 7.
So why is the work W net not just 4?
It's 40.
Oh,
4 times 10. Oh, flip. Which other bit? The other way. There isn't another way here. Oh, you mean the non-conservative one? W? WNC. The non-conservative one. I might have it done for you. I'll show you. So you get 7. So did you get this way?
how do you do it the other way, sir?
The NC way. If you wanted to do it the other way, let's do this. Let's do this. If you wanted to do it the other way, you could say, let's try. WNC is equal to delta EK plus delta EP. You agree? Now what's WNC? It's the work done by the non-conservative forces. How many non-conservative forces are there? Only one. So WNC is going to be equal to WF. Any force, applied force, is non-conservative. So it's going to be equal to WF, and WF is just going to be F delta X cos theta. Is going to equal to, let's just say, half mv F squared minus half mv I squared. We know that delta EP is equal to 0 because it doesn't move up or down. Yeah? So that can fall away. Now here you've got 4 times 10 times 1 is equal to a half mvf squared minus half. Sorry, what's m? M is 2. So you've got a half.
So why is the EP net 0?
Because it's moving horizontally, it's not moving up or down. So half times 2 times, what's the initial velocity was 3. 3 squared. And you'll see that's exactly the same equation. And then when you solve it, you're going to get VF equal to 7. Say that again? Because that's the formula. They asked me to do it the other way using this formula. WNC is delta EK plus delta EP. Yeah, but that's why it's equal to 0, because it doesn't move up or down. Okay. So do you agree you get the same answer? No, but it doesn't matter which way you do it, you should get the same answer. All right. So now, Slightly harder one. Now it's got friction. Initial velocity when it passes S is 2 meters per second squared. Same thing, same method. You just got an extra force to consider. Go for it.
So can you quickly go back to our slides?
This one or the other one?
This one.
The NC one.
This one. This one you can use that F resulting.
Yeah. Very similar example. Now you just got a second force to think about. Getting somewhere now.
Yes, sir.
Okay, you got to write your formulas down. And you get nothing for the answer if it hasn't got units. Got to write your formulas. Even if you're working on the laptop, that's your choice. That just means your typing is going to improve. Yes?
So, at the bottom for VF, is it not m dot s to the minus 1? Isn't velocity in minus 1 not x?
Yes, you're right. How are you getting with this one?
I've got this one.
Okay. It's meters per second, not squared, to minus 1. Thank you for the correction. I'm losing it.
So,
Yeah.
can you just look at this?
Yeah.
My rounding here. I think I lost a mark in the exam for
Would your teacher really be so mean?
So if I get this answer,
Yeah.
and then I say 2 root 6, and then I say 4.898.
No, you can't.
Dot dot dot. And
Yes,
then
yes.
round, dot dot dot, and then round off.
Okay, so we're not going to give you a mark for an answer inside the question, only for the final answer. So is that the final answer?
No, so I don't know what.
That is the final answer,
But then if you wanted me to round it off, would it be fine if I?
Is this the final answer?
4.9, yeah.
Yes. Good. So you only round it off at the end. Have we got a number yet? 4.90. So I worked out the net force because I always think that's easier. Then I use the net force to work out the net work. And the net work is just going to be your net force times delta x cos theta. So
when would theta in this case be 180?
if you were considering F2, the work done by F2, it's moving that way, F2 is that way. So now I've got my force is 2, my net force is 2, I've worked it out. And I've got delta x, the distance, cos theta between the net force and the displacement is 1. Initial and final velocities. I know the initial was 2, and so I work out 4.90. Mr. Pillay, did you get it right? I'm impressed. Well done. Feels good when you get it right. Yes, and harder. So it only gets harder by if we put this on a slope. Then you got friction and a component. No. What they normally do though is that there's two movements. Often there's moving with constant velocity and then it starts to slow down. So you have to consider two sections of the thing separately. Right, can we move on? Here, I've just worked out something just for fun. I've worked out the work that is done against friction. Okay? If you just worked with a frictional force only, you would have worked out there was minus 20 joules of work done by friction. Okay? And so the work done by friction is minus 20 joules, if we'd asked you that question, and the work done against friction is 20 joules. All right. You must be able to do that. You must be able to work out the work done by friction. Okay, so we're nearly there. We're nearly at the end. This is just the revision of what you did in grade 10 with pendulums. All the energy at the top is converted to all the potential at the top is converted to kinetic at the bottom, and so you can work out the velocity of the falling object, which interestingly does not depend on its mass. And you know that anyway, because if you drop an object, its velocity doesn't depend on its mass. Its velocity only depends on, in the absence of friction, only depends on the strength of gravity and the height.
I'm not why it's hypothetical, because there's always friction if you drop a mass.
There is, but the reason we work with hypothetical situations, especially at school, is because it's baby steps. Obviously, if you want to go into the real world, that's when it gets complicated, but you only do that at varsity. So at varsity, if you carried on with this kind of thing, you do applied maths. And then applied maths, you start saying, okay, now we know how to do it without friction in the ideal world. Okay, now let's add friction. And it's just getting there slowly. If we threw it all at you in one go, you'd never get there. But once you're happy with this kind of stuff, we're saying, okay, now when we consider friction, and you just add in a few things. They talk about rocket science. I probably mentioned it to you before. That saying, well, it's not rocket science, is true. Rocket science gets massively complicated because not only do you add friction, but the friction changes as the speed increases. Mr. Pillay, you're bugging me now. So the friction changes as the speed increases, but also your mass changes as the speed increases.
So is it like rocket science to a degree, or is it like rocket science engineering?
There is space engineering. I don't know if you're talking about, when you get to those levels, it gets so broad that you have to specialize. So I don't know how you actually, and if you talk about rocket science, there's facets of rocket science. Now, Mr. Pillay, you're still bugging me. And one of the reasons is you're not looking at me. I'm talking to you, you're looking somewhere else. 2 strikes. All right, so there's the basic theory. Here's an example. A person of 60 kilograms lifted to a height of 30 meters on a slingshot pendulum and released, calculate the maximum speed. If you don't know how to do it, look at the previous page. Go for it. Look at the previous page. It tells you exactly how to do it. I've given you the mass. I've given you the height. Why didn't you fill it in? You can't get left behind.
Is it at 0 meters?
Yes.
Depends on that looking at.
Because well, no, but you're working it out. The height is the height difference between here and there. Because it can't fall any further. Well, you're assuming. You're taking them as a point, actually. This is actually a grade 10 level question. You need to bring your calculator. Because you haven't got that in the exam. Got a number? How many people get 24.25? 1, 2. Connor? It's a grade 10 question. Right? It's not even a grade 12 question. 24.25.
So you started there.
What is the bottom of the thing?
Sorry?
On the previous page it says v equals to square root 2gh. What is that?
That's the equation you're using.
Velocity equals to...
Yeah. Okay. V equals square root of 2gh.
What if you just did the mgh equals to
It's fine.
mv squared? Oh, is that fine?
Well, you got to be careful because remember I said to you. So guys, when you do questions like this, they like you to show that the energy at the top, the mechanical energy, is potential plus kinetic, and the energy at the bottom is potential plus kinetic. Remember, you can't say the potential is equal to the kinetic. It is true that the potential at the top is equal to kinetic at the bottom, but you have to specify that. You can't just say potential is equal to kinetic.
If I just say E
You'll lose your mark for that. Sorry?
E top equals E bottom.
Yes.
Yeah, that.
Because now he's going to start going up, so he's going to lose kinetic energy in order to gain potential. That's what happens to as soon as you go past 0, you now start going up. To gain potential, you have to lose kinetic. You can't gain any potential if you haven't lost kinetic. No, this is at the bottom. Before he starts moving up, 90 degrees. Yeah. So I think we'll have to leave it there, chaps.